Okay, welcome back to EE210B, where you are going to learn more and more about how to perform inference over networks. I will continue with the background material. I should be done with it hopefully soon, and then we will start moving deeper into the course, okay? But this material is really important because you are going to be using it regularly throughout the course. So I would like to make sure that at least all of you have heard of it and at least know that it exists somewhere so that you can go and check on it when you need it, okay? So today's topic, I will be talking about Lipschitz conditions. Okay, if you remember, in my last lecture, let's move on here. What's happening? So the slides don't want to move. Strange. Okay, so just a minute. I need to ask someone to help. So. Where is the... Hi, Carlos, the slides are not working on my... They are not moving back and forth. Yeah, where is Christina? I'm giving a lecture, but they don't move. Yeah. No, here. I usually use this. It doesn't work. Do I have to use this instead? I can use this instead. Okay.
Probably you can do right now.
I cannot, right? I know. I can't.
No.
Thank you, Carlos. Let's close the door. Okay. Okay. So welcome back to EE210B. Okay, this is lecture number 7, and we will be talking today about Lipschitz conditions. Okay, so this is still part of the background material that I would like you to be familiar with, because we'll be using this material extensively in the course, okay, so that at least you know where to refer to when you need to know more about it, okay? Now, if you remember last time, I talked about mean value theorems, right? That was Appendix D in the text. The material for today is based on Appendix E, okay? So what we did last time, I started with a function, I started with a function g of z, real valued function. It wasn't necessarily convex. I just required it to be differentiable, okay? And I derived relations that told you provided you with expressions for the increments in the function and increments in the gradients of the function. Remember, these were similar to a Taylor series expansion, where on the right-hand side you have an expression that tells you exactly what the expansion is, rather than terms that you would usually ignore, right? So if you remember, the mean value theorems led to relations like this. Okay, so G is a function which is not necessarily convex, and I would like to expand it around Z0, right? So I have a small perturbation around Z0, and what this expression tells me, it tells me that G at that point, I can express it in terms of G at Z0 in this form, right? The left-hand side is equal to the right-hand side plus a term here, right? So that's what the mean value theorem allows you to do, and that term depends on the integral of the gradient vector of the function, right? And this is an integral over a scalar parameter, and delta z is by how the size of the step. Remember, we did this last time. So this was for the function, and the relation below it is for the gradient vector itself, right? So we have one relation for the gradient vector, and therefore here you will have the Hessian, and the first relation is for the function itself. Now, remember, the gradient relative to z, which is a column, by definition is a row vector, right? That's why you have delta z appearing on the left so that the dimensions match. And remember again that the Hessian matrix in the real case, when z is real, is m by m. And then we had the complex version of this when z was complex, right? The first relation was the same. The second relation was very similar, except that I had to extend these gradient vectors. I had to define a block vector containing the gradient relative to z, the gradient relative to z star, here and there. And the Hessian matrix in that case was 2m by 2m, right? And this was also extended, right? So this is what we did last time. These are useful relations, mean value theorem relations. They tell you how to expand a function or its gradient around a particular point, and they tell you exactly what the difference is, right? So what I'm going to do now, I'm going to take this a step further. What if my function is convex? Can I say more? Okay, so I'm going to work these relations a little bit more, extract more information from them, because the cost functions that we'll be minimizing in this course, they will be convex. So for these cost functions, there is more I can say from these relations. For example, if the function g of z is convex, let's say strongly convex, it will have a unique minimum, right? If it has a unique minimum and that minimum is z0, the gradient at z0 will be 0, right? Very good, okay? So I can replace this expression for the gradient up here, right? The second equation gives me an expression for the gradient. I can replace it inside the first integral. I will end up with an expression that tells me what the increment will be in terms of the Hessian now, right? I can use that. I will be using that very soon. And by following this argument, okay, we will be able to bound, we'll be able to do two things. We'll be able to say how big this increment can be. We'll be able to bound it from below and from above. Not just give an expression to it, but we'll be able to say it will, the norm of this increment lies between these two bounds, number one. And we will be able to say, to assess the size of this term, okay? So these are additional pieces of information that I would like to derive for convex functions, okay, starting from these relations. Okay, so today's lecture is an application of these relations to the particular case when I have a convex function, for both cases when z is real and complex, fine? So let's start, okay? So let's start with the case when z is real, okay? And g is convex. So in that case, I'm going to take this z0 to be the minimum, okay? In that case, the gradient evaluated at z0 plus delta z, you come here, if I replace this delta z by t delta z, this delta z here will be replaced by t times delta z, and this delta z here will be replaced by t times delta z, right? So if you do that, you get exactly this relation, right? I haven't done anything, okay, anything strange so far. All I did, I started with a function g of z, and I assumed that I picked z sub 0 to be c z sub 0, the minimum, right? Remember my notation when I put the o on top, that argument refers to the minimum of the function, right? So if I pick my z sub 0 to be the minimum, right, then the two relations I gave you before combined give you this result, right? So far so good, right? This is for a general function g of z evaluated at the minimum or expanded around the minimum, okay. So now, very often in this course, and I will be talking more about this later, okay, we'll be dealing with cost functions whose Hessian matrices will be bounded. Okay, now if you remember when I defined strongly convex functions, if g of z is nu strongly convex, I showed in a previous lecture, right, that this is equivalent to saying that the Hessian of that function is lower bounded by nu I. Remember that? That was an equivalent condition for strong convexity, right? The Hessian matrix of the function, no matter what z is, will always be lower bounded from below by nu I. Let's assume that it is upper bounded as well from above. Okay, we'll encounter many situations in this course where the cost functions that we are interested in satisfy a condition like this. So now I have a cost function whose Hessian matrix is bounded from below and from above. The lower limit, I'm calling it nu. The upper limit, I'm calling it delta I, right? You understand what this notation is. This is a matrix less than or equal to another matrix. This means if you subtract, if I call this matrix capital A minus capital B, the difference is non-negative, non-positive definite, right? That's what the less than or equal to 0 there says, right? All the eigenvalues are less than or equal to 0, okay? So if you come back to this relation, which is general for any function with second order derivatives, right? If you come back to this function, you see I'm telling you that the Hessian is bounded by delta. So if I compute the norm, right, of both sides, this delta, the norm of the Hessian is bounded by delta, right? So that becomes a constant. You take it out of the integral. You have a double integral with a t, right? You integrate twice, right? You integrate over t squared over 2. You integrate over r. So you end up with t squared over 2 between 0 and 1. That's 1/2, right? Okay. So because of that, you end up getting, and remember, you have a delta z here and a delta z there, right? This is an inner product becomes the norm of delta z squared. Okay, so this is very immediate to get, that because the Hessian matrix is bounded from above, okay, because the Hessian matrix is bounded from above, we are going to get this statement here, okay, we are going to get this statement here, right? If you go back, by the way, if I go back here, even though I wrote norm, you see I don't need that. Okay, I don't need that. I don't need to take the norm. Why? Because this Hessian matrix is non-negative definite, right? So the quantity on the right-hand side is always non-negative, okay? It's always non-negative, right? If you remember that, if I have a matrix A, this is a matrix A, we'll be talking in the next lecture about some basic matrix results, and this is hopefully one that you know. If I have a matrix A which is symmetric and non-negative definite, its eigenvalues are between lambda min and lambda max, right? Then you know that X transpose AX will be between lambda max, norm of A squared, and lambda min, norm of A squared, right? Okay, this is related to something called the Rayleigh-Ritz characterization of eigenvalues. We'll be talking about it in the next lecture, but I believe you may have seen it. Okay, so this is what's happening here. You see, I have a vector and its transpose, and I have a non-negative definite matrix here in the middle. Okay, so this quantity here will be upper bounded by delta, the norm of delta z squared, and there is the 1/2, and lower bounded by, what's lambda min in this case? Because the Hessian matrix, my Hessian matrix, in this case, is upper bounded by delta by assumption, and lower bounded by nu, right? Okay, so this nu is definitely smaller than the lambda min of the matrix, and this delta is larger than the lambda max of the matrix, right? Okay. Yes.
The norm of x of the
No, sorry. No, yes. Norm. This is norm of x. Sorry, norm of x. Okay, norm of x. Okay, and here also, I didn't need to write norms, right? Just to keep it clear. Okay. So it's not difficult for you to conclude that this result holds, right? Okay. So all I have shown so far is that if I have a strongly convex function g of z, and therefore its Hessian matrix is bounded from below because of strong convexity, I'm assuming in addition that's bounded by above, from above by delta. Okay, if this happens, if the Hessian is between two bounds, then the increments will be between two bounds, right? Fine, between two bounds. That's what we have shown so far. A similar result will hold when z is complex as well. I'll mention that briefly later. Now, why is this result useful? So this is the first conclusion. Okay, so why is this result useful? And remember, this z0 here is the minimum, right? The 0 is the minimum of the function, okay? So one implication, I used to have g of z minus g of z0. So I moved g of z0 to the other side of the inequality, right? So one implication is that every strongly convex function can be sandwiched between two quadratics, right? You see, this is a quadratic as a function of z, quadratic in z. And this is another quadratic in z, right? So every strongly convex function, you can bound it, right? From below by a quadratic function of z, and from above by a quadratic function of z, right? If you have some strongly quadratic function here, you can find a quadratic from below and a quadratic from above that always bounded. That's one conclusion, useful conclusion, okay? Sorry? Oh yeah, sorry, this is just, I did not draw it with precision. I'm just trying to convey the idea, right? Okay, because when z is equal to z0, right, they both have the same value. So at the optimum, they touch, okay? Right, so if you want to be precise, if this is the minimum, right, so you will have a quadratic from below and a quadratic from above. This is more difficult to draw, but that you get the idea, okay? That's what this result is trying to say, okay? So far, so good, okay? Now, let's take this a step further. There is another conclusion I can get from this result, which will be very useful for us later, okay? And the second conclusion will hold if I introduce an additional assumption. So far, I assume that the Hessian is bounded from above, right? Bounded from above. Besides the strong convexity, that's a given. If the Hessian is bounded from above, you get the conclusion I showed you before, that the function g of z can be sandwiched between two quadratics, fine? Number two, let's assume in addition, okay, that the Hessian matrix is Lipschitz, okay? So what does that mean? I sometimes refer to this by saying that the Hessian matrix is smooth enough at the minimum, okay? What does that mean? It means if you are at the minimum and you perturb it a little bit, the change in the Hessian matrix, right, is bounded, okay? Is bounded by the size of the step that you took, okay? That's what I mean by saying that the Hessian matrix is smooth, and this is what it means to say that the Hessian matrix function is Lipschitz. Okay, that's what Lipschitz mean. Okay, if you have a function in general, if you have a function f and you want to say that it is Lipschitz, this is essentially what we say. Okay, that there is some constant. Here I called it kappa, let's say x, L. That this holds for some constant L, okay? for all x and delta x up there, okay? That's the definition of what a Lipschitz function means. Here I'm saying that I want the Hessian matrix of the function to be Lipschitz. What this means is that the function is well behaved such that if I move a little bit away from the minimum, the Hessian changes only in proportion to this step, okay? Very good. Now,
Which norm of the matrix are you?
sorry, here I'm using the Euclidean norm, okay? So I'm using the two-induced norm. All the definitions I will be using are relative to the two-induced norm. What is the two-induced norm of a matrix? Again, in my review of basic matrix results, you will know what it is, but I assume that you have heard that before. The maximum singular value of a matrix, right? That's a norm. So when I write the norm, the two norm of a vector, you all understand what it is. The two norm of a vector induces a two norm on the matrix, which is the maximum singular value of the matrix. So what this means, the maximum singular value is upper bounded by some constant times the two norm, right? Okay. Now, I'm saying here that I would like the Hessian matrix to be locally Lipschitz, okay? Locally Lipschitz. What that means, okay, or Lipschitz continuous if you want to be more precise, okay? But I will not be pronouncing all these words all the time, right? So, locally means I would like this property to hold close enough to Z0. That's good enough for us, okay? Later I'm going to show you actually that if you require this condition to hold locally, it will turn out to hold globally as well. That for any Z and delta Z, for any delta Z, this will hold for a different kappa. I will show this later, okay? Let's not worry about that for now, okay? So let's assume for now that my cost function satisfies this. For example, if g of z were a quadratic function, quadratic, does it satisfy this condition, yes or no? Because the Hessian of a quadratic function is independent of z. Right? So that you will get always 0 on the left. So a quadratic function automatically satisfies this. But there are, of course, other functions that satisfy this. Some of them you will do in your homework problem, okay? Okay. So if this is the case, what is the second conclusion I can get from this, okay? To say that the Hessian is Lipschitz, I mean locally Lipschitz continuous, okay? To say that it is Lipschitz, essentially you are saying that this quantity on the left is equal to the second quantity, this is the last equation on the slide, plus some small perturbation, but the size of that perturbation is not bigger than the norm of delta z. What this notation, big O, means is that this quantity here, right, is upper bounded by some constant times this norm. Okay, so that's what means that the difference is of the order of the norm of delta z. The difference is something that is some constant times the norm of delta z, upper bounded by some constant times the norm of delta z. Okay, that's what this means. Okay, so do you see how this follows from this? Okay, okay. Now, if this is the case, remember what I showed in the previous lemma? Okay, what did I show here? I showed that the increment involves an integral of the Hessian, right? But right now I showed you, if the Hessian is smooth enough, the Hessian at this small update around Z0, I can relate it to the Hessian at Z0 itself, plus a small error, right? Okay, now if I put the Hessian of Z0 here, you see? So let's clean this so that you can see where I'm going with this. Okay. So here you will get the Hessian at Z0 plus an error which is of the size of delta z, right? So when you compute this integral, you will get two terms. Okay, what will you get? You will get delta z transpose times the Hessian at Z0 times delta z, right? Plus norm of delta z squared coming from this inner product that times something of the order of delta z, correct? Correct? So the conclusion is, look here, this is a weighted norm, right? This is a vector times a non-negative definite matrix. Actually, in this particular case, it is positive definite because the function is strongly convex, right? So this is a weighted norm, right? There is 1/2 that I forgot that comes from this t. Okay, there is 1/2 in front of this, correct? So the conclusion from this is that the increment is equal to a weighted norm of delta z weighted by 1/2 the Hessian at z0, right? Plus an error term which depends on the cubic power of the norm of z, delta z. Correct? Because this is a squared, this is right, this is a cubic power of norm of delta z. So the second conclusion that I wanted to say is, that follows from the first lemma, is actually I can find an expression for this difference. I can tell you exactly what the value, not exactly, I can approximate well what the value of the right-hand side is. This is it. It is a weighted norm of delta z. I wrote the delta the other way around, but I know you understand. Right? This is delta, not, okay? So delta z squared, this is a weighted norm, right? With the Hessian. So you find the Hessian at z0, okay? This norm, this quantity here is by how much g is going to change. And the size, and this is a good approximation for that because the size of the error will depend on the cubic power of delta z. If you take a very small step, the cubic power of that will be much smaller, right? So this is a good approximation to this degree. You understand? So this is the second conclusion that I wanted to mention to you. Okay, so if I put these things together, okay, so this is what the calculation I did on that slide. And this notation stands for this, right? Okay. So this is the conclusion. Okay, this is the second conclusion, right? So you see, for convex functions, I was able to say, to extract these two pieces of information from the mean value theorem, okay? That this increment is bounded between two bounds. I know how the smallest it can be, and I know the largest it can be, number one. And not only that, I can find a good expression for it. I can tell you, and I can tell you the size of the error as well. And this is a good approximation for it up to this amount of error, right? And the important thing to note here is that no matter what your strongly convex function is, okay, no matter how it looks like, the change in the function is a squared Euclidean norm, a weighted Euclidean norm, okay? And this is very useful. Because what this says is later, when we want to assess the performance of algorithms that are performing adaptation or learning or estimation over networks, okay, very often you would like to know, when you are updating an algorithm, what are you doing when you are updating an algorithm? You are moving from one estimate for the minimizer to another estimate to another estimate to another estimate. You are moving from one estimate to another location, right? And you would like to know, to assess by how much this algorithm is improving, for example, at every step, right? So what this result is telling you is that a good way for you to assess that is to simply compute a quadratic function of the step, right? A quadratic function of the step. The nonlinearity of the function itself doesn't come here, right? It only enters through the Hessian matrix, okay? Fine. So we will be using this result in that way when we do analysis later in this course, okay? Very good. Fine. This is an example. A quadratic function. G of z is quadratic, okay? So it's convex. If C is symmetric and positive definite, it's convex, right? The Hessian matrix is 2C, okay. The Hessian matrix is 2C, right? So it's bounded between 2 lambda max of C and 2 lambda min of C, right? So nu is 2 lambda min, delta is 2 lambda max, right? Okay. So if you find what the value of this function is at its minimum, okay, and you can bound it between delta over 2, delta z squared, right? And g at z0, nu over 2, delta of z squared, right? That's what we showed before. This delta is lambda max of 2c, right? Which is 2 lambda max of c. So delta over 2 here will be replaced by lambda max of c. And similarly, nu over 2 will be replaced by lambda min of c. Right, that's the calculations in this example. You understand where we are going? Okay, I'll come back to this expression, but I just want to show you. You see, this is delta, this is nu, therefore the Hessian is between these two limits. If you apply directly the results of the theorem I showed you, okay, the value of the function at the minimum, you can find the minimum. How do you find the minimum? Compute the gradient, set it equal to 0, right? This is the gradient. Set it equal to 0, you find the minimum. Evaluate the function at the minimum, here it is. And then from the lemma, the function will be bounded by this and will be bounded by that, right? Now, of course, in the quadratic case, you don't need to go through these lemmas. These calculations, you can do them directly, right? You can do them directly because you know the function. It has a very simple form. And for the quadratic function, by the way, for the quadratic function, this is a completion of squares argument. You can always write it as the minimum value plus a quadratic term that involves the difference between z and the optimum value of g of z, right? For any quadratic function. If you have any quadratic function like this, you can always express it as, this is just algebra. You can verify that this is the case. Z minus z0 transpose c z minus z0. Right? This is just some algebra. You know what g of z0 is. It is this first term. Right? So if you expand this, you get that. So you can see right away that g is g of 0 plus the maximum this can be. The maximum this can be is lambda max, right, of c times the norm of z minus z0 squared. Okay? So you don't need dilemmas in this case, but I'm just showing it as an illustration. Okay? That's one. Okay, and then the second component of the lemma is that I have an expression for the increment, right? What did the expression say? It will be it will be the squared norm of the step times here, weighted relative to the 1/2 of the Hessian. The Hessian was 2c, so it becomes c. Now the lemma said that this is approximate, but for the quadratic case, this is actually exact, right? Because for the quadratic case, g minus g of 0, right? You can see this is the norm of z minus z0 relative to c with weight c. It's exact, okay? Anyway, so this example illustrates, right? Okay, so for quadratics, for a quadratic function, this is exact, okay? But the lemma is more general than that, okay? For example, you can apply the lemma to the logistic function. You will prove in one of your homework problems that the logistic function, the regularized logistic function, is strongly convex, right? So you can derive and apply relations like this to the logistic function, okay? And other functions as well, okay? Fine? Okay. So that's that. All I did, I started from the mean value theorem, and I showed you that I can say more if my function is convex, right? I can bound the increment between two bounds, and I can give you an expression to the increment which is accurate to the order of delta z cubed, right? That's what we did. And similar relations will hold when z is complex. That's the later part of this lecture. Okay, so I'll go through that a little bit more quickly because it's very similar. But before I get there, I want to provide an interpretation of what does it mean for the Hessian matrix to be smooth. Remember, how did I define it to be smooth? I said the Hessian is Lipschitz, right? That's what I mean by saying the function or the Hessian matrix is smooth at the minimum, okay? I said that, sorry, in this part I'm actually going to show you two things. One is I'm going to revisit the smoothness condition on the Hessian, okay, and show you that that local smoothness condition is actually leads to a global smoothness condition. That's one thing. The second thing I want to show you is this result, okay. is this result. I assume that the Hessian is upper bounded by delta I, right? That was a condition I needed to be able to arrive at the conclusions I got. I want to show here that saying that the Hessian is upper bounded by delta is equivalent to saying that the gradient vector is Lipschitz with delta. Is delta Lipschitz, that's the language we use, is delta Lipschitz. Okay? So you will hear Lipschitz a lot in this course, okay? But it's nothing more than saying, when I say the gradient is Lipschitz or a function is Lipschitz, it just means that the increments in the function are upper bounded by some constant, the increments in the argument, that's all, okay? Fine? Now, so I want to show that this implies this and this implies that. By the way, intuitively, it's not difficult for you to see the connection. How do you define the derivative of a function? Let's say in the scalar case, f of x plus delta x minus f of x over delta x, right? That's the derivative. You see, if you take this norm and you divide it by that norm, right? It is, and then take the limit as z goes to the other z, it's almost like computing, right, the norm of a second order derivative, right? So it's not difficult for you intuitively to see that these two things should be related. The proof will make this argument precise, right? Okay, now, so can you see an advantage why it may be advantageous to state that condition in this form and not in the first form? Because sometimes the function may not be second order differentiable. It may just be first order differentiable. So sometimes it's more convenient to state the condition just at this level rather than go all the way to that level. You understand? So that's why I would like to show that these two things are equivalent, so that if you see it stated only as equation 21, you'll understand that this is actually related to the other condition that we are using, right? Okay. So this is the next lemma. Okay. Saying that the Hessian is upper bounded by delta is equivalent to saying that the gradient vector itself is Lipschitz by the same amount delta. Okay, fine? And then we'll have a similar result in the complex case as well. I'm just, okay, stating these facts. So let's prove this. So this is an if and only if statement, right? To prove it, you have to prove it in both ways, right? If the Hessian is bounded, then the Lipschitz condition holds. If the Lipschitz condition holds, then the Hessian is bounded, right? You have the proof in the notes. I can mention it quickly here. Okay, so let's assume that the Hessian is bounded, okay? We know that it's actually bounded from below as well. At least by 0, it's bounded from below, okay? Now, consider this function h, which is the gradient of g. Okay, h is the gradient of g, right? So this is a vector, because the gradient relative to a row is a column vector. So h is a column vector, okay? And apply the mean value theorem to this column vector. Nothing so far, right? Just apply the mean. The difference is the integral of the gradient of h. Well, the gradient of h will be the Hessian of g, right? Okay. So here I just wrote down the mean value theorem. This will now be the Hessian of g, right? Okay. So if this is the Hessian of g, and the Hessian of g is bounded by delta, also by 0. For strongly convex, actually, it's bounded by nu. But this result holds even for just purely convex functions, okay? Then, if you take the norm now, right? So this norm here will be upper bounded by delta times the norm of z, right? The norm of the difference of the z's. That's exactly the Lipschitz condition, right? So if the Hessian is bounded, then it's obvious to show that the norm of the difference of two gradients is bounded by delta times the norm of the difference of z's. So one direction is obvious. Let's prove the other direction. Okay? Here it is, okay? So let's prove the other direction. So now I'm assuming that the function has Lipschitz gradient, and I want to show that the Hessian is bounded, right? The opposite. Okay. So let's introduce this function, which is the gradient evaluated at z plus t delta z. So f of t is a function of a scalar variable, right? We did this last time. So if I differentiate it relative to t, you differentiate the argument here, the inside relative to t, you get delta z. And then you differentiate the function itself, you differentiate the function itself relative to z, you get the Hessian, right? Fine so far? Okay. So f of t is just a function of a scalar variable. So the derivatives of that function is your usual notion of derivatives, right, from calculus 1, right? So if I evaluate the function at two different points, t plus delta t, okay? So this is the value of the function at t, okay? And sorry, is there something missing? Oh no, okay, I'm just writing down the definition of the function, right? So this is f of t, right? And this is f of t plus delta t, okay? But the function, by assumption, is Lipschitz. The gradient is Lipschitz, right? So this is the gradient at one point, this is the gradient at a displaced point. So this will be upper bounded by delta times the size of the displacement. The size of the displacement is what? Delta t, delta z. That's the difference, right? Okay. So if the gradient is Lipschitz, I know so far that this is upper bounded by that. Divide by delta t. So you get that the ratio is upper bounded by that. And take the limit as delta t goes to 0. Okay? So this will be, right, the norm, right? The norm of that derivative, right? F is a function of a scalar, but f itself is a vector, right? Okay? Very good. So far, this is what I have, okay? This is what I have. If you go back, okay? Remember, the derivative of the function is the Hessian times delta z. So I'm going to replace this norm by the Hessian times delta z, right? This is what I have shown so far. I have shown that the Hessian times delta z, the norm of that is upper bounded by delta times delta z, right? So I've shown that a matrix times some x, think about it like this, is upper bounded by delta the norm of x, right? Let's just write a and x to make the notation simple. I want to conclude from this that this implies that this a, which is non-negative, is actually upper bounded by delta, right? This is what I want to conclude from this. Okay, very good. So if you continue, I'm going to square both sides, okay? You see, I had the norm of ax squared would be less than or equal to delta squared, the norm of x squared, right? Fine? Okay. Now, what is here the norm of ax squared? This is x transpose A. Remember, A is symmetric because it's a Hessian matrix. Times ax, so this becomes a squared x, is less than or equal to delta squared x transpose x, right? So this tells you that x transpose a squared minus delta squared I x is less than or equal to 0 for any x. So this tells you that this matrix here, this relation is true for every, right? It's true. So the a squared, and remember, a is symmetric and non-negative, positive definite or non-negative definite, right? So from this you can conclude that a is upper bounded by delta, right? Okay? So we proved that lemma, okay? Here it is, we proved this lemma, okay? So if you go back, you see, so this lemma only requires G to be convex, not necessarily strongly convex, fine? So whenever I say the Hessian is upper bounded or the gradient is Lipschitz, now you know that these are similar statements, right? Equivalent statements, right? They are equivalent, of course, when the derivatives, both of them exist, right? But choosing this formulation might be more useful for us if the function doesn't happen to be twice differentiable, okay? Very good. So now let me extend these results quickly to the complex case. Oh, sorry, before that, I have to show you the global result and then I'll extend it to the complex case, okay? So the second result I want to show you is this. Remember, I assumed before that the Hessian is locally Lipschitz, right? By that I meant that it satisfies a relation like this, close to the minimum for all delta, right? That's what we meant by locally Lipschitz. Close to the minimum, the Hessian changes according to this relation, right? Only in proportion to the size of the step. I want to show actually that because of that, if your function is strongly convex, that local Lipschitz condition actually holds more globally. I want to show that relation 30 holds. What does relation 30 says? Any step you take away from Z0 will satisfy the Lipschitz condition. No matter how far away you move from Z0, the increment in the Hessian will never be more than in proportion to the step you took. It's not just local, it's global. And the kappa prime here is either the kappa that you started with locally, it's the maximum of two quantities, all of them depend on your problem. Delta, upper bound, lower bound, epsilon is the small neighborhood, right? So what I'm trying to say, there exists a kappa prime, which is constant, independent of Z, such that this holds. Fine? So let me show you, okay? We are going to use these results later when we study how well algorithms perform over networks, okay? So that's why I'm mentioning them here, okay? We're not going to go through the proofs again, but you can always revisit them. So let's prove this statement, okay? So what do I want to show? Okay? I want to show that this holds for every Z. Okay? So let's do the following. Let's take that difference. Okay? By the way, ZO is the minimum of the function, right? Just keep that in mind, okay? Now, and let's take this, multiply by any vector x transpose and x from left and right, so you get this, right? Now, the Hessian is upper bounded by delta, lower bounded by nu, right? So the second term here, right, I replace it by something smaller. The first term, I replace it by something bigger, right? So the first line is upper bounded by the second line. Are you following? Okay. And then I group these two terms together, okay? So I'm telling you that, remember, this is a symmetric matrix, right? This matrix here is symmetric, okay, because I'm dealing with real data, so this is probably a typo here. Okay, in this first part, everything is real, okay? So symmetric. So that matrix is symmetric. You see, I have shown that x transpose AX is less than or equal to delta minus nu x transpose x, right? So for any x, so it means that this matrix is less than or equal to this times the identity, right? Okay. So this is one first conclusion, okay, so far. I haven't yet finished my argument, but all I have shown so far is that the norm of this difference is never more than delta minus nu. And remember, delta is larger than nu. Okay, so let's use this property now to establish the lemma. Okay. Let's do this. Pick any z inside the small region around z0, right, where the smoothness condition we already know holds by assumption, right? Pick a z inside that region. Okay. Then the norm of the difference we already know satisfies that, right? But what was kappa prime? Kappa prime was the maximum of kappa delta minus nu over epsilon. So kappa prime has to be larger than or equal to kappa, right? So this is always true. Fine? Okay. So if z minus z is inside that region, relation 34 always holds. If z is outside that region, then I use this property here that I just proved. Okay. The norm is less than or equal to delta minus nu. So I divide by epsilon and multiply by epsilon. And again, this quantity here right? This quantity here is upper bounded by kappa prime, and this quantity here is upper bounded by the norm of z minus z0. So either way, you get the same relation, right? And you establish the lemma. You understand? Okay? So these are not difficult properties. Just convince yourself that they make sense, because later we are going to use them. And if you forget where they came from, you can come back and follow the argument. They are not difficult arguments, okay? Fine? Okay, so what I proved here is that if the Hessian matrix is locally Lipschitz, for a strongly convex function, actually it is globally Lipschitz, and we will use this later in our analysis, okay? So this is a useful property, right? I could have given you this as a homo problem, right? Okay, so let's extend these results quickly to the complex case, okay? I don't need to go through all of the arguments because you already know the extensions are not that difficult. Okay, so the first statement, remember we have a mean value theorem, right? We have two versions of the mean value theorem for complex arguments, right? Increments of g and increments of the gradient of g, right? Okay, just like we did before, you can show again that let's assume, before we continue, that my function is, okay, complex valued now, meaning z is complex valued, and the function is nu strongly convex, okay? Now, if the function is strongly convex when the argument is complex, remember this means that the Hessian matrix is bounded from below by nu over 2, not the nu, right? Remember I mentioned that this 2 will live with us, and this is the difference between real arguments and complex arguments, and I'm going to go around it by introducing a type variable that I'm going to call h. So in the future, I will always write in nu over h, and h will be 1 when your data is real, h will be 2 when your data is complex, so that you don't have to keep remembering this, right? But for now, because I'm doing things separately, I'm separating them, okay? So if your function is strongly convex, it will be nu over 2. So let's assume that it's bounded from above by a similar factor delta over 2, just to be consistent, okay? In the complex case, okay? So if you go back and you use the mean value theorem, the argument is very similar to what we did before, right? You will get that the increment is upper bounded by delta over 2 normal, right? How do you prove this? All you have to do work with the g of v, right? You introduce the vector v, which contains the real part and the imaginary part of z, right? So your function becomes a function of a real argument. And then you apply the lemma that we showed before for this function of real arguments, right? For this function of real arguments, you will have that g at v0 plus delta v minus g at v0 will be upper bounded by the norm of delta v, right? What will go in here, right? And will be lower bounded by the norm of delta v, right? What will go in here? So here should go an upper bound on the Hessian of g, right? What should go here and there, right? These bounds are the ones that will appear here, right? So if you remember last time I showed, okay, last time I showed that if the complex Hessian, I showed you the relation, by the way, between the Hessian in the real domain and the Hessian in the complex domain. Remember that there is a d star relating them, okay? A d star relating them, okay? And because of that, if this is bounded by delta over 2, and remember d star is equal to 2i, the 2 will cancel, so the left-hand side will be bounded by delta I. And from below it will be bounded similarly by nu I, right? So bounds in the complex domain that involve delta over 2, nu over 2, they become bounds involving delta and nu in the real domain, right? Okay? So these bounds here, okay, will be delta and nu. And then you go back to the, right, this is what I'm showing here. So this is the bound. And then you can write down right? If you go back here, this will be delta over 2, and this will be nu over 2, because this is what we derived in the lemma, right? Remember the integral of t that gives you t squared over 2, right? Integral between 0 and 1, that's how this 1/2 came from, okay? So that's the result here, okay? And again, it means that you can sandwich your function between two quadratics. Okay, very good. Now, the second conclusion that you get from this result, what was it? The second conclusion that I can tell you that G, right, if you remember, I showed you that this, I can write it as this, right, plus I had some weighted norm, remember? Weighted norm with the Hessian at Z0, right? This was in the real case. What is the analog of that in the complex case now? Okay. Now, if you remember, how did I get that result? The result I wrote here on top. Okay. I got that result by integrating, right, an expression that involved the Hessian. Okay. In the complex case, that Hessian is 2m by 2m. Okay. And the mean value theorem, where the Hessian term appears, requires me to extend the delta z's, if you remember. Okay, so if you just repeat the same argument I did before, I'm just calling your attention to why these things come up, right? If you go back to the argument I had before and repeat it in this case, you will get a similar expression. You see, this is a weighted norm of what? Of the extended delta z, that's all. Okay, the extended delta z, because the mean value relation in this case will involve these extended vectors. Are you following? Right, the extended vector delta z, because this Hessian is 2m by 2m, so this will have to be 2m by 1. Exactly the same argument as before, you will arrive at this expression, okay? And the difference will be of the order of the cubic norm of delta z. You could write delta z extended, but the norm of delta z extended is related to the norm of delta z, because they are delta z star, right? Okay? Yes.
In the error term,
Yes.
the multiplying matrix with the order of the error term might not be the identity matrix.
Sorry?
The multiplying matrix with the order term, the error term of order of...
What this is saying that error term, its entries, right? By the way, that error term is a scalar, right? It's a scalar because g of z is a scalar.
Yeah.
So the error term is a scalar. So the size of that term, right? The size of that term is of the order of the step cubed.
Yes, so my doubt is that when you're doing the integration, you're doing the integration of a matrix term, and then outside you have delta z transpose, and then
Yes, yes.
So if the matrix is not identity, it could be some different.
No. We did this argument precisely, right? Let's go back. Here, right? We did this argument exactly here. Right? We replaced this.
Yes.
Okay.
Yeah, this is a matrix.
Right. This is a matrix, right? So we replaced it by a Hessian plus something of the order of delta z, right? Okay. Now, I don't really care about the structure of this. It's just some error, right? Whose size is of the norm of delta z. Okay? So this gives you the norm of delta z under integration. And then delta z transpose with delta z gives you the other delta z squared.
Okay.
Right?
So you mean the error matrix, each term of the error matrix is of the order of...
That's what this notation means, yes. That's what this here, that's what this notation means. Each term of the error matrix here is of this order. Is that what you meant?
Yes.
Okay, yeah. Okay. Okay. Okay, I'm moving forward just to get back to where we were, right? So you all understand where this comes from? I don't need to go through the argument. The argument is in your notes, okay? This is a trivial extension of what we did before, okay? Here it is. You have the argument in your notes, right? And that's how you get delta z, delta z, delta ze. Because you see, you can work in the real domain, using 1/2 of the real Haitian, right? And then transform the real Haitian, right? Let's say if you multiply by d star, divide by 1/4, you did not change anything, right? But then use the fact that d times h times d star, that's the complex Haitian, right? So just carry out the arguments. And that delta v times d star is the delta u which contains the delta z. Just carry out the arguments, you arrive at the expression. Okay, so I will let you read that. It's not very, very difficult. And then I repeat the same example I had before. In the quadratic case, what is the Haitian here? Block diagonal C, C transpose, right? Block diagonal C, C transpose. Again, if you perform a completion of squares argument, you can write the minimum value plus z minus the minimizer C, z minus the minimizer, okay? And again, okay, the maximum. So the delta here is lambda max and the nu is lambda min because this is C, not 2C, right? So the Haitian here will be bounded by lambda max of C from above, lambda min of C from below. So you can use these values, right? And remember, we assume that this is bounded by delta over 2, so delta has to be twice that, and the nu has to be twice that. So you just plug these expressions into the lemmas, and you get the bounds for this problem, right? You get these bounds for these problems, which, like I explained before, you could have derived them exactly. You don't need dilemmas for the quadratic case. You just work with the quadratic function, right? And even this expression for evaluating the increment, it's actually an exact expression in the quadratic case, okay? Fine? Okay, so that's what I wanted to cover in this lecture, okay, on Lipschitz conditions, okay? Again, you can continue. Like I said before, okay, if I will just mention these statements because this is similar to what we did before, okay, I don't want to bore you, right? Assuming that the Haitian is upper bounded by delta over 2 is the same thing as saying that the gradient vector is Lipschitz, right? Delta over 2 Lipschitz, okay? Proof, I proved it in the real case. How do you prove it in the complex case? Work with G of V, right? G of V is real. Write down these relations in the real case and then transform them to the complex case, okay? So that's the argument I have, okay, in my notes. You work with G of V, okay? So I'm not going to go through that just because it is not that difficult, okay? You can read it, okay? That's the proof. And then similarly, if you assume that the Haitian is locally Lipschitz, then it turns out to be globally Lipschitz for the same kappa prime defined down here, right? Again, proof. You can apply this to the real version of G, G of V, right? And then transform it, right? The Haitian in the V domain, we know how it relates to the Haitian in the Z domain. And then you get this relation, okay? That's what I have done in the notes, okay? Fine? So that's what I wanted to discuss with you today, right? Move from the mean value theorems and extract a little bit more information about what I can say in the convex case, right? So I derived a few statements here, which you will see applied often during our analysis of algorithms over networks. Okay, so let's take a short break and we'll continue later. Okay. Okay, welcome back to EE210B. So this is our last lecture on the background material. Okay, and today I will be reviewing some matrix results, which I hope most of you are familiar with. If not, this is a good reference for you to learn about them. Okay, so I will be stating many facts, and I expect many of you to know them. If you don't know them, again, this is a good reference. And I will not be going through proofs, right? This is just to collect in one place many of the results that will be used throughout this course, okay? So I will give you an overview of some fundamental matrix results and linear algebra results that we use, okay? These are references for this lecture. The first reference is Appendix F from the text that you have. The second reference is from a chapter that I wrote for a book. It has additional results. We may not use many of them in the class itself, but you may need some of these additional results, for example, in your homework problems. Okay, so that's why I'm mentioning them. Okay, so if you need to solve problems, let's say involving the block maximum norm, that's a good place for you to learn more about the block maximum norm. Okay, I will be using only some of its properties here, but if you need additional properties, this is a good reference for that. Okay, so let's start. First, Kronecker products. I assume most of you know what Kronecker products are. Okay, so what are Kronecker products? So assume you have two matrices A and B, A with individual entries, sorry, let's go back, A with individual entries Aij, B with individual entries Bij, okay? The matrices do not need to be of the same dimension. So what is the A Kronecker B, which we denote by this symbol? It's a bigger matrix. How do you get this bigger matrix? You replace every entry of A, here it is, A11, you replace it by a matrix. You replace it by A11 times B, A12 times B, and so forth. That's what the Kronecker product is. You enlarge your matrix in this manner, okay? So then the dimension of this bigger matrix will be Nm by Nm, okay? Kronecker matrices are very useful. You are going to see that in this course. This is the definition, okay? Now, they have many useful properties, and we'll be using some of these properties. Let's assume that the lambda I of A and lambda J of B denote the eigenvalues of A and B. Okay, so A and B here are square matrices with eigenvalues lambda of A, lambda of B, and with singular values sigma of A, sigma of B. Okay? Then the following properties hold, and I would like to highlight some of them. Okay, some of them that we'll be using. Okay, for example, 7. What would the eigenvalues be of this bigger matrix? The eigenvalues of the Kronecker product is the pairwise product of any combination of eigenvalues of A and B. You have n eigenvalues for A, m eigenvalues for B, right? There are how many ways of multiplying them together? All of these give you the eigenvalues for the Kronecker product, right? Nm of them, right? You understand? Of course, this requires a proof. You can't try to prove it, right? I'm not proving it, I'm just stating it. It's not difficult to prove, okay? It's not. By the way, a similar conclusion holds for the singular values of the Kronecker product, okay? So that's one useful result we will be using. The first few results are trivial. Number 2 is very useful. Okay, number 2 is very useful. It's a factorization result. Okay, if I have the Kronecker product of AC with BD, you can write that as a normal product of A Kronecker B with C Kronecker D. Useful result. Again, it requires to be proved. I'm stating it. Okay. Another result that will be very useful for us is result number 12. Very, very useful for us. Okay. What it says is this. What is the VEC notation? VEC. What is VEC of a matrix? You see a matrix here, you have a square matrix, right? Let me draw it normally here. Okay, this is a square matrix. It has columns, right? So vec of A, you will take the first column and then put the second column underneath it, the third column. You'll get a big vector. You vectorize the matrix. That's what it is, right? If your matrix is n by n, what's the size of vec of A? N squared by 1. So what that property 12 is saying is the following. If I have the product of three matrices, and I want to vectorize it, how is the vector of this product related to the vector of the center matrix? That's what this result says. Okay, very useful, and we will be using it. It says you compute the canonical product of B with A, B transpose with A, B transpose with A times vec of C. Okay, remember this property. Again, you can prove it easily. It's not that difficult. 13 is a special case of 12, right? X and Y are two vectors. X is a column, Y transpose is a row. So C is 1, right? So there is no vec C, C is 1, right? And you will get Y canonical X there, okay? Fine? So you need to be familiar with some of these properties, especially number 12 and number 7, okay? And of course, the other properties are also very useful. So this is one, okay? And there is something else called the block canonical product. We'll be using it as well, block canonical product. So let me define it. Before, I had A and B, and I worked with the individual entries of A and B. Now I have A and B, but they have block entries. So their entries are submatrices, okay? So A and B now have block entries, okay? This is for A, and this is for B. Okay, they have block entries. And then I use this notation for the canonical product. Okay, A canonical with a little b. Okay, people use different notation, by the way, so you don't get confused if you look into the literature. This is the notation I'm using for the block canonical product. Okay, how do you define it? Okay, this is how you define it. So the block canonical product will be a matrix with blocks, a block matrix. And each one of these blocks, each one of these, okay, is defined in terms of the traditional canonical product. So for example, the ij, right, the ij, pick one of them here. You will take the ij block of A and compute its canonical product with every block in B. Right, of course, the sizes become, right, this size, but that's how you define it, okay? That's how you define the block canonical product. You work with blocks, with submatrices, okay? This is just definition. Just if you write down a simple example and do it yourself, you'll be able to see what's going on, okay? Now, the block canonical product also has a useful interpretation, a useful properties. For that, I need to introduce the B-vec operation. Before I explain to you the vec of some matrix A, what was that? You put the columns one under the other. The B-vec is a block version of that, okay? B-vec, oops, of A. Now the matrix has blocks, right? Has blocks. So what you do, you vector, so this is A. It has blocks, A11, A12, A21, right? So you vectorize this block, that's a column. Then you vectorize the block underneath it, that's another column, right? So you're not putting one column under the other, you are putting the vector that comes from the subblock one below the other. This is a vector. So you treat the blocks as if they are the entries, you vectorize them and put them one under the other, okay? Now, before I show you the properties, why is this useful? Take this matrix here, matrix A. Assume all of these are scalars, just to keep things simple for now. What would be the vec of A? The vec of A would be, you take the first column of A, put it here, right? The second column, put it underneath. The third column, fourth column, right? Okay, so that's the vec operation. I just want to show you why the BVEC and block canonical products are useful. Look on the right-hand side now. The block vector operation, I take a block, let's say I'm working with blocks of this size, and you vectorize it. The other block, right? The third block, the fourth block. So what you see, the structure that's present inside the matrix is preserved in the block vectorization form, right? I know these entries come from the same block, they stay together. They are not together over there, right? So there are advantages for working with the block vector operation and the block canonical operation. Sometimes, not always, sometimes, and we will encounter some of this later, okay? But apart from that, very similar properties to the regular canonical product. For example, look at property 8, which we will use. Property 8, BVEC of a product of 3 block matrices, how it is related to the BVEC of the center matrix. The same property, right? You just replace VEC by BVEC and canonical product by block canonical product. Look at property 6, similar to what we did before. The eigenvalues of the block canonical product is the product of all of the possible eigenvalues, right? Look at property 2. Very similar, right? You just work with, right, property 2, where you have here the canonical product of the, right, of AC with BD, and you factor it, okay? Fine? Have you seen canonical products before? Okay. So that's it. That's all I want to share with you about canonical products and block canonical products. And that they have a list of useful properties, particularly property 8 here and the equivalent property, and also property 6 here and the equivalent property. Okay, this will be useful for us. Of course, we will also use property 2 and few others, but these are the keys, the key ones for us. Okay. The second topic I want to review with you is the concept of vector norms and matrix norms. Of course, in the previous lecture, I already used some of these concepts, assuming that you know them. If not, this is your chance to learn some of it, okay? So, vector norms, most of you are familiar with the Euclidean norm, which is the third one in this table, right? The Euclidean norm of a vector. This is the notation I'm going to be using. Right? You square the entries. In the complex case, magnitude squared, you add them up and you take the square root of that, right? Okay, that's the Euclidean norm. But there is also the one norm, and there is also the infinity norm of a vector. What is the one norm of a vector? You add the magnitudes of the entries, not the magnitude squared like you have here in the third case. You add the magnitudes of the entries. That's called the one norm. Okay? What is the infinity norm? The largest magnitude, okay? The largest magnitude, that's the norm of the vector, okay? If you have a vector 1, 2, 4, the infinity norm is 4, right? The one norm is 1 plus 2 plus 4, okay? And then, of course, you can define the p norm for any p larger than or equal to 1. You can show that this is also a norm. The pth power of xk, the magnitude of xk, and then you take the, right, the pth square root. Of course, you should show that these are norms. You know, for something to be a norm, it has to satisfy certain properties, right? Okay, so for something to be a norm, for example, the norm of any vector has to be non-negative always, right? The norm is 0 if and only if the vector is the 0 vector, or a matrix. The same thing applies to matrix norms. I will be talking about that, right? If you scale the vector, this should be equal to, right? These are properties that, for the triangle inequality, right? If you add any two vectors, right? This property has to be to hold. This is the triangle inequality, and then there is a submultiplicative property, the norm, right? This is the less than or equal to the product, okay, of norms, something, okay? So there are certain properties that you cannot define any function and say it's a norm. It has to satisfy certain properties. All these norms satisfy these properties, okay? Now, we can also define matrix norms that satisfy similar properties, but for matrices. You can also measure the norm of a matrix, okay? Now, Let me show you a table and then I'll come back. You can define the one norm of a matrix, the first line. What's the one norm of a matrix? Okay, you compute the one norm of the columns, right? Each column is a vector, and you pick the maximum among them, the maximum column sum, or maximum absolute column sum, understand? That's what the one norm of a matrix is. The infinity norm, you compute the infinity norm of the rows, and you pick the maximum among that, okay? The P-induced norm, that's what it's called, P-induced norm, let's say pick P equals 2, P equals 2. Why this is? Because this is the norm that's induced by the 2 norm. That's how we call it, okay? If you are using the 2 norm, P is 2, then this ratio, the maximum this ratio can be. What is this ratio measuring? Let's say X is the input to your matrix, AX is the output of the matrix. This is measuring how much gain you get in going through the matrix, okay? The maximum that can be serves as a norm, okay? When P is 2, this is called the 2 induced norm. When it's P induced norm. These are induced norms, okay? For example, you can show here. When P is 2, you can show that this is the maximum singular value of A. Okay, so this is what I wrote on the previous slide. The maximum singular value of A is the 2 induced norm of A. That ratio you can show. So the maximum singular value of a matrix is a norm. Okay? Fine? Now, there is this useful property which we are going to use, that over finite dimensional spaces we say norms, whether they are vector or matrices, they are equivalent. They are equivalent. What does it mean? Equivalent norms mean if, for example, if this is one matrix norm and this is another matrix norm, let's say the 2 norm and the 1 norm, right? Or the 1 norm and the infinity norm. Pick any 2 norms, right? Norms help you compare matrices to each other in terms of size, right? In vectors to each other in terms of size. What this statement is saying is that norms are equivalent. What that means is this. Whether you measure the norm of A relative to little a or relative to little b, right, there are always constants that relate them. Okay, so there are always constants, Cu for upper, Cl for lower, okay, such that any norm is sandwiched between the other norm. So if the matrix is small relative to one norm, it is small relative to the other norm. That's what this is essentially saying. Right? Norms are equivalent. Okay? If you bound a matrix relative to one norm, you can get bounds for that matrix relative to another norm, because there exist C's, C lower and C upper, independent of A, such that relations like this will always hold. Okay? So keep this in mind, we'll use this, and it will be useful in some of your problems as well. Okay? Now, another useful result is the following. Assume I have a matrix B, and assume I tell you this matrix is stable. In discrete time, a stable matrix means all the eigenvalues are inside the unit disk, magnitude less than 1. Okay? You understand what I'm saying? Okay. So what can you say about the norm of the matrix? Does it necessarily follow, for example, that the maximum singular value will also be less than 1? Okay? Right, it depends. It's not necessarily the case. If a matrix is stable, it doesn't necessarily follow that the norm of the matrix is less than 1. Okay? It doesn't necessarily follow that it is less than 1. Okay? Okay, here what you have is a very useful matrix norm, because sometimes I have a stable matrix. Okay? Look here. Assume I give you a recursion like this. Fine? Start from any initial condition for the vector x and keep applying b. If I tell you b is stable, where do you expect x to go? 0, right? Now, how did you conclude that? How would you prove that? No, simpler than that. Okay, okay. What you said is correct, but if you iterate many, many times, right, you will get something like this, right? And because B is stable, B to the n will go to 0. How do you know that? For example, like she said, if you introduce the Jordan decomposition of B, right, T times J times T inverse, where J are the Jordan blocks, have the eigenvalues on the diagonal, right? All of them will be less than 1, right? B to the n, right? You will see that all these powers of the eigenvalues will go down to 0, and this will converge, right? This is one way to prove it. For example, if B is diagonal, let's say, just diagonal, keep it simple and stable, right? By examining the powers of these lambdas, this goes to 0. Now, if I want to prove this result instead by using norms, I have this, the norm of this, from the submultiplicative property of norms, I have this inequality, right? I have this inequality. So far, so good. But if B is stable, does it necessarily, for example, let's assume I'm using the 2 norm for vectors, 2 induced norm for matrices. It doesn't necessarily follow that the 2 induced norm for B is less than 1, right? If I could come up with a norm such that if B is stable, that norm is strictly less than 1, then I will get that relative to that norm, right? If I can find a, let's denote that norm by some index rho. If I can find a norm such that if B is stable relative to that norm, the norm of B is strictly less than 1, you end up concluding that this recursion is always decreasing, right? And ultimately will converge. Okay? So what I'm saying here, that's why I call this a useful matrix norm. Sometimes you need a norm like that, okay? So this is to show that such a norm exists. If your matrix is stable, such a norm exists. How? First of all, let's introduce the spectral radius of B. This is a notation that's very important. Rho of B, okay, is the size of the largest magnitude eigenvalue. The closest to the unit circle. That's called the spectral radius of B. If a matrix is stable, the spectral radius is necessarily strictly less than 1. Fine? Okay. Introduce the Jordan decomposition of your matrix, right? Take B, write it as, let's say, T, J, T inverse, where this J is block diagonal, right, with the Jordan blocks. You know what Jordan decomposition is, right? Okay? The Jordan blocks have lambdas on the diagonal, ones underneath the diagonal, right? And pick any epsilon and define this diagonal matrix D. For any epsilon, define this diagonal matrix D. N is the size of B. Epsilon, epsilon squared, epsilon to the n. Then define this norm. This is a norm, okay? Define this norm. What is this norm? You give me any matrix A. I'm going to multiply it by TT inverse that come from B, DD inverse, which I chose, okay? It's a simple exercise for you to show, and this is the one norm of that. It's a simple exercise for you to show that this is always a norm. It satisfies the properties of norms that we talked about before, okay? You can show that. And in particular, if A happens to be B, the row norm of B will be strictly less than 1, okay? Because if you put B here, okay, if you put B here, B is T, J, T inverse. So this T cancels that, this T cancels that. You will get the one norm of T, J, okay? And if you compute the one norm of this product, and the J's have only ones and lambdas, and being multiplied by epsilon, epsilon inverses from left and right. If you compute the one norm of this matrix, a simple exercise, you will find out that this one norm is always less than 1, strictly less than 1. Okay? I don't show the argument here, but it's a simple exercise, okay? So just remember this, that if a matrix happens to be stable, there exists a norm defined by the matrix, right? Defined by the Jordan decomposition of the matrix, which you can use to measure the size of other matrices, and it has this useful property that for B itself, its norm will be strictly less than 1, okay? Very good. These are the properties that any norm has to satisfy, right? Like I mentioned to you before, okay? Okay, so here it is, okay? You can show that the one norm that I just defined for B, that the row norm of B will be sandwiched between its spectral radius and spectral radius plus epsilon. Since you are free to choose epsilon, since the spectral radius of B is strictly less than 1, you can always choose an epsilon to make sure that this is strictly less than 1, right? That's what I meant, okay? Here. Okay. Now I'm going to skip this part. You can read it. We don't need it. But here I'm showing that this norm that we just defined actually is also an induced norm. You can show that this norm that I just defined for the matrix, it is an induced norm. Induced means you can get it from a vector norm in this manner, where you define the vector norm in the manner I'm showing here, okay? We don't need this result, so I'm going to skip it. You can read these arguments in the notes, okay? I have the proof there. Let me move to another useful norm, okay? This is the block maximum norm that I mentioned at the beginning of this lecture. If you need to know more about it, you can go to that second reference I mentioned. Here I will only mention facts that we will need, okay? So this is another norm. Very often we will be dealing with block vectors. So you might say, I talked about the block Kronecker product before. Block vectors now. So why I'm talking about block quantities? When you are dealing with networks, and each agent in this network is trying to estimate something. If you collect all these iterates, all these estimates into a big vector, you have a block vector. Each part of it is coming from one agent. So block vectors, block quantities will arise naturally in the context of networks. That's why block Kronecker products and block vectors and block norms are useful. Okay? You understand the motivation? So what is the block maximum norm? This is how it is defined. So I have a vector which has block vectors, okay? So x1 is a subvector, x2 another subvector, right? So these are subvectors, the smaller vectors. They could be scalars in an extreme case, okay? So now each one of these subvectors has a 2 norm, right? Has a 2 norm. The maximum 2 norm among them is the block norm. Remember, if all these x's were scalars, what would this norm be? If all of them were scalars, the infinity norm, right? Because you pick the maximum, that's why I use infinity here, right? And B because it's for block, right? You understand? That's the definition of the block norm. Just keep the vectors as subblocks and pick the maximum 2 norm, okay? Now, you can also define an induced norm that you get from it, okay? How? Assume I have a matrix A. X is a block vector, right? So A also will be a block matrix, has blocks, okay? Consistent with the block structure in X. So let's say block, let's say 3 by 3, right? And X has 3 blocks, right? So assume you have a matrix A which has blocks and a vector X which has blocks. So you can also define the induced block matrix norm like this, right? The maximum of the ratio, of the gain, right? This is a norm, okay? And we call it the block maximum norm for the matrix, okay? I always use the calligraphic notation for block quantities, block matrices. This is consistent in my notes, so that when you see something you know, especially in the context of networks, like I'm just saying that this has a block structure in it, okay? Okay. Now, the block norm has the block maximum norm has many useful properties, okay? Here I'm only stating some of them. There are many others which you can get from the second reference, okay? But one which is particularly important for us is this property B here. And I believe there is a D. What does B say? If I have a block diagonal matrix, so D1, D2, Dn are blocks on the diagonal, okay? Then the block maximum norm of D is the spectral radius of D. What is the spectral radius of this D? The maximum spectral radius among the individual spectral radii, right? Each one of these has a spectral radius, the max, okay? So this is one property, okay? The block maximum norm is the spectral radius of D, useful property. Property 1, property A is just saying that if I take a block matrix and multiply by block unitary matrices, you see there here U is diagonal, and these U's, block diagonal I mean, and the U's themselves are unitary, okay? Here, block diagonal, and these are unitary. Okay, so block diagonal with unitary, or in this, yeah, unitary, because this is the general meaning that UU transpose is identity. That's what a unitary matrix means, right? Then the block norm does not change under U. Okay? Not any unitary U, block diagonal unitary U. Okay? It makes sense, right? If you take a block vector, multiply it by a block diagonal with U's. So each subblock is multiplied by the corresponding U. So the 2 norm of each subblock is not changed because it's being multiplied by a unitary matrix, right? So it makes sense. Now, the property which is very useful for us, before that, let me mention property C. Assume A has this structure, A chronicle I. What is A chronicle I? A is a matrix, has individual entries, little a, right? So you take A11 times I, A12 times I, and so forth, right? At every location of the matrix, you put an I. You repeat the entries on the diagonal. That's what A chronicle I is. This matrix will come up many, many, many times when you study networks, okay? If the matrix is left stochastic, this is a terminology, it means the rows add up to 1. Okay? If the matrix, okay? So it means that A transpose 1, this is the vector of 1s, is equal to 1. That's what it means to be left stochastic, okay? Take a matrix, so the A transpose, so you take the row of A transpose, that's the column of A, times 1. So the columns add up to 1, sorry, the columns add up to 1, right? Okay, so it's just terminology. Like a probability matrix, when the entries are all probabilities that add up to 1. Okay? These matrices, the block maximum norm is 1. Okay? And then property D, which is very important, and you will see why it's very important. If I have any block diagonal matrix and modify it from left and right by left stochastic matrices like these, you can never increase the spectral radius, right? You can never increase the spectral radius. Now, why is this result important? When you study, I'm just motivating it, I'm not showing it. You are going to see it later. When we study the dynamics of networks and how networks evolve, the dynamics will be controlled by the spectral radius of some block diagonal matrix. So if that spectral radius is bounded by 1, the dynamics will be stable. When you take agents and you connect them by a topology, what a topology does, as you're going to see, it will always modify the dynamics by some left stochastic matrices. So what this result is saying, I will use it later to show that if you connect your agents in certain ways, if it happens to be stable, you will never destroy the stability. And that will come from a useful result like this, because the spectral radius will never go up, regardless of A1 and A2, and this will correspond to how the agents are connected to each other, okay? I'm just motivating the result way ahead of time, but this is where I'm going to use it, okay? Okay, fine. So that's all I want to say about block maximum norms. There is more about it, but that's enough, okay? Jensen's inequality. This is very much related to convex functions. Have you seen Jensen's inequality before? Okay, so what Jensen's inequality is, there are variations of it. Okay, here I'm just showing you 2 or 3 variations that are useful for us. Okay, so assume I have coefficients that add up to 1. They are all non-negative, they add up to 1. Okay, and I have a collection of column vectors, W, then, and F is a convex function. F is a convex function. Okay, F is a convex function, okay? remember how did we define convex functions? We said if you evaluate f at any combination, right? Convex combination of 2 points, this has to be upper bounded by the corresponding combination at the points. Remember that? If you have a convex function, if you evaluate here, you evaluate there, right? This is the line. Okay, this is Z1. This is Z2. This is any point in between. The value of the function at this point is lower than the value of the function there, right? Remember, this is how we define convex functions. So this relation 26, which is one form of Jensen's inequality, is an extension of this, right? It's saying if you evaluate your function at any convex combination of a collection of points, you will be upper bounded by the corresponding convex combination of the values of the function. That's a useful way for you to remember it. This is just extending the definition, right, of the convex function, right? Extending that property to this case, okay? In particular, by the way, if your function f of x happens to be the norm of x squared, then this is saying that the norm squared of a combination of wk's is smaller than the combination of the individual norms, right? Squared norms. That's, okay, an application. You can apply it for other norms, let's say the fourth norm, because it's a convex function and so forth, right? Because we are going to be using, you see, if I didn't have a 2 here, triangle inequality will give you something like this. Jensen's inequality gives you with a 2. Sometimes you want a bound with a 4, right? Or with other powers, as you're going to see. Jensen's inequality saves you. That's essentially what this says, okay? So this is one form of it. There is also the stochastic version of it. You see, if A is a random variable, what's the definition of the expected value of A? It is the integral, right? It is the integral, the integral of A, f of A, dA, something like that, right? This is like a convex combination of many values A's, right? So the value of the function at infinitely many combinations, right, of A is less than or equal to the combination, right, at the, so that's the natural extension of it. If your function is convex, this is what you get. If your function is concave, concave, by the way, means the negative of it is convex, right? This is convex, this is concave, right? It will, correct? Did I draw it wrongly? Now, yeah, you have to figure out which is which. Okay, so one is convex and one is concave. Okay, so, okay. That's Jensen's inequality, okay? A few other things. I'm just mentioning these results, okay, so that you know they are there, and when you need them, you can come back and use them. These are two useful theorems that I will be using. Wiles' theorem deals with the following. Assume I have Hermitian matrices A prime, delta A. A is Hermitian, you perturb it by delta A, you get A prime. How are the eigenvalues related to each other, right? Remember, this is the title of this section. If I change matrices, if I perturb the entries of a matrix, how are the new eigenvalues related to the old eigenvalues? This is a difficult question to answer in general. You see, take a polynomial, perturb the coefficients a little bit. How are the roots of the new polynomial related to the roots of the old polynomial, right? That's a similar question here. There are some results that allow you to bound the variations in certain cases, and these will be useful. So let's assume the eigenvalues are ordered. 1 is the largest, n is the smallest. Because these matrices are Hermitian, the eigenvalues are real, so I can order them, okay? They are Hermitian. This theorem is for Hermitian matrices, okay? So they are ordered. And then what the theorem says is if you perturb A like this, add delta A to A, so it's a different matrix, it's an A prime. Let's look at the nth eigenvalue of A prime. It will be close to the nth eigenvalue of A. It will be a perturbed version of the nth eigenvalue of A. Remember, they have been ordered. You can say that it will never go beyond the nth eigenvalue of A plus the maximum eigenvalue of the perturbation you added, okay? And this is the nth eigenvalue plus the smallest perturbation you added, right? Delta A, this delta A, okay, has the largest eigenvalue, smallest eigenvalue, okay? The upper bound, you add the largest value. The smaller bound, you add the smallest value. So this eigenvalue will always continue to lie within that interval. That's what this is saying, okay? If this is your original lambda n, okay? So you add lambda 1 to it, so it comes here. And, okay, let's draw it. Okay, well, the eigenvalue, delta A is Hermitian, but its eigenvalues can be positive and negative, right? So this can be positive, this can be negative, right? So whether you draw both of them on this side or one on this side, one on the other side, depends on the relative sign of these things, right? For example, let's take a simple example. Let's assume delta A is simply a multiple of the identity for some small delta, right? So then this is just delta. And this is just, well, in that case, it's easy, right? In that case, I don't even need this theorem, okay? You just shift the eigenvalues by delta, right? Let's take this other case, which is the non-negative definite case, which is more interesting, okay? So in this case, so I'm adding lambda max of delta A, lambda min of delta A, but all of them are non-negative, right? So you can see here that if I perturb A by a non-negative term, its eigenvalues will increase, right? Will increase, right? Because lambda min, you are adding something to it, right? You are adding lambda min of delta A, which is non-negative, lambda max of delta A, which is non-negative, right? You get the point, right? It all depends on the eigenvalues of delta A, right? And this is ultimately the relation, right? Just remember, there is a theorem there. If you perturb Hermitian matrices, it tells you how the eigenvalues are perturbed. This is one. Another theorem is Gershgorin's theorem, a very famous theorem, okay? And this is what it says. Assume I have a matrix. Okay, I have a matrix, here it is, okay, and I have the diagonal elements of the matrix, ALL, okay. Around each one of these diagonal elements, I put a circle, okay. Around this, I put a circle, okay. Around this, I put a circle, another circle. What is the radius of that circle? The radius of that circle, you take the sum of the elements on that row except the diagonal element, okay? So for this, you take the sum of the magnitudes of all of these entries except the first one. That determines the radius for this. And this similarly for all the other entries. So you will have a collection of Gershgorin circles. What the theorem says is that the eigenvalues of the matrix will lie inside the union of these circles. It's an interesting theorem. If you compute the union of all these circles, that's where the eigenvalues will be. And then there is a variation to this theorem, which says if this union of circles happen to consist of two disjoint parts, let's say this one has L of them and this one has the remaining ones, then L of the eigenvalues will be in this set, n minus L of the eigenvalues will be in this set. That's what this theorem says, okay? Yeah, no, if you have a collection of n sets generating this subset here, which is disjoint from the remaining, and remember, you have the number of circles is the size of the matrix, right? If L of them are disjoint from the remainders, then this set will have to have L of the eigenvalues, and this set will have the remaining eigenvalues. This is what this theorem says, okay? We are going to use this result to prove one of the key results in our analysis. Okay? So there are two more results I want to share with you. Okay. One pertains to Lyapunov equations. Have you seen Lyapunov equations before? Okay, so let me show you this very quickly. this is an equation. This is called the Lyapunov equation, discrete time Lyapunov equation, because there is the continuous time, also called Stein equation. You see, this is an equation satisfied by the matrix X. And you want to find X. A is A star, and Q is Hermitian. I give you A and Q, and I ask you find X. We'll encounter equations like this in our analysis. That's why I'm mentioning it. These are called Lyapunov equations, okay, or discrete time Lyapunov equation. Okay, now I'm going to say that the matrix A is stable if all of its eigenvalues lie inside the unit disk. Okay, this is the discrete time definition of stability. In discrete time, right, the matrix is stable if all of the eigenvalues are inside the unit disk. Now, how do I solve this equation? Is there a unique X? What can I say about X? It turns out there is a theorem, not difficult to prove using Kronecker products. You see, for example, let's apply the VEC operation to both sides. I'll give you a very quick proof. It is here, but I want to give it to you more intuitively. Let's take the VEC operation of both sides. So VEC of X minus, okay, VEC of A star. This is property 12 from table 1, right? VEC of a product of three matrices, it is A transpose, Kronecker, A star, VEC of X, right? So you get VEC of X here and VEC of X here. So VEC of X is multiplying A transpose, Kronecker, A star, equals VEC of Q, right? Right? So this became now a linear system of equations. A linear system of equations. VEC of X is a vector. VEC of Q is the right-hand side vector. The coefficient matrix is this, right? Very good. Now, what are the eigenvalues? The eigenvalues of A transpose, Kronecker, A star, they are given by the products, pairwise products of all of the eigenvalues of A transpose, A star. All these products will be strictly less than 1 in magnitude. Why? Because the eigenvalues of A are stable, right? If you multiply any two of them, the product will be less than 1. So this matrix on the left is invertible. Doesn't have any eigenvalue, right? All these eigenvalues are less than 1 in magnitude, and this is all ones, right? So the eigenvalues here are always non-zero, right? So this matrix is always invertible, so X is unique. X is unique, given by the inverse of this times VEC of Q. So the solution is unique when A is stable, number one. And number two, the solution is Hermitian, because if you take X star, conjugate, Q star is Q. X star minus A star, X star A. X star satisfies the same Lyapunov equation, which has a unique solution. So X star has to be equal to X, right? Okay, this is that. And one final thing, okay, so that's what I showed. The solution is unique. It is Hermitian, okay? And one final thing, I just showed you that VEC of X is given by I minus A Kronecker A inverse VEC of Q, right? I wrote the A Kronecker A as F. Let's unwind this. You see, I minus F inverse. This is equal to the sum of F to the N, right? Remember, for scalars, 1 minus X, 1 over 1 minus X is 1 plus X squared when the magnitude of X is less than 1, right? For matrices, the same thing holds. I plus F squared, etc. This is I minus F inverse when F is stable. You can prove it. Okay? So I minus F inverse is F to the N VEC of Q. And then I put back here what F to the N is. Okay? Because when you take power N, you put the power inside. This is one of the properties. And then use the definition of VEC. This becomes VEC of that. So X is the sum of A star Q A, right? So you get this series representation for the solution. This is another way to write the solution, okay? Very good. Now, there is a similar result. I'm going to skip this one and move on to the last result. This is called the continuous time Lyapunov equation or Sylvester equation. In a similar way, using Kronecker products, you can show it has a unique solution. Here, you will need A to be stable, meaning the real part of all of its eigenvalues have to be negative, okay? It will have a unique solution, and it is Hermitian. I'm going to skip that. The argument is very similar, okay? I already defined what left stochastic matrices are. The columns add up to 1. It means this. Right stochastic matrix, the rows add up to 1. Doubly stochastic matrix, both of them hold together. Rows add up to 1, columns add up to 1. Okay, so this is one property. Stochastic matrices have the following properties which are very useful. The spectral radius is 1. Okay, if a matrix is stochastic, its spectral radius is 1, meaning all eigenvalues have magnitude less than or equal to 1. Okay? That's number one. Okay? Number two, if your matrix happens to be primitive, and we are going to define this later, okay? For now, just remember this. A matrix is primitive if I can find a power such that all the entries of that power are strictly positive. That's what a primitive matrix means. I'm going to define this later, okay? So if A happens to be primitive, then the spectral radius is equal to 1, and there is only one eigenvalue that meets it. All other eigenvalues will have magnitude strictly less than 1. Okay? All other eigenvalues will have magnitude strictly less than 1. Okay? So here it is. There will only be one eigenvalue at 1. Its eigenvector, I call it P. Okay? I call it P. You can always normalize the entries of the eigenvector. I'm going to normalize them to add up to 1. This is what this notation means, right? 1 times P equals 1. There is a famous result called I mentioned it here, okay. Well, Perron-Frobenius theorem. I did not mention the name here.
Yes, Perron was last. Next slide.
Next slide. Yeah, this theorem. Okay. If your matrix is primitive and stochastic, it has a single eigenvalue at 1, and it has an eigenvector P, right? You can normalize it to add up to 1, and the theorem asserts that all the entries of P are strictly positive. This is not always true that the entries of your eigenvector are always positive. Okay, so we are going to be using this fact later, okay? I'm not proving this, I'm just stating it, okay? I'm skipping these, I don't need these results for now. You can read them, and the final result I want to show you is this, and then we are going to break, okay? The final results are, there are two recursions that we are going to encounter. I'm just stating the results here. You see, if I have a recursion, this is a deterministic recursion. The new value is upper bounded by a coefficient times the old value plus a driving sequence. And if the sequences A and B satisfy certain conditions, okay, certain conditions, the values of A is between 0 and 1, B is always non-negative, the value of A is add up to infinity, okay, meaning this series diverges, but B over A converges. Under these conditions, you can show, and this is one homework problem, you can show that this sequence converges to 0. This is a very useful result. We are going to be using it. Okay, so if you have time, you can try to establish it. I'm just stating it. This is the deterministic version, and then there is the stochastic version under expectation. Okay, under expectation. So this is conditional expectation of the U's given the past, and this is the U's. You can show that the mean goes to 0 under similar conditions, and U goes to 0 almost surely, okay, with probability 1. Just remember that we have these two recursions, okay, and one thing I skipped here in the deterministic case, when you have this recursion in the deterministic case, it's not only that the U go to 0, but if your sequences A and B are chosen in a particular way, here it is, A is 1 over I of the form some constant over I, and B some constant over a power of I, then you can show that they go to 0 at a particular rate, and you can identify these rates. For example, this goes to 0 at the rate 1, or let's say if P is 1, at the rate 1 over I, or at the rate 1 over I squared, right? So you can say at what rate these values go down to 0, okay? So this part may have been quick, but all I really need you to know is that these lemmas exist. When I get to them, I will remind you of these lemmas, and you will see why they are useful and how we are going to apply them, okay? And when I get to the Lyapunov equations also, I will remind you of the lemmas, and you will see how we are going to use them, okay? So this is a general overview of some basic matrix results I will be using during this course. I did not prove most of them. Some of the proofs are there in the appendix. You can go and read them. I just wanted you to get to know that these results exist, okay? So I think this is enough for today, and I will see you next time, okay?